take a look at some things that we talked about in lesson 1 and some concepts that you know from last year. So we looked at inverses yesterday, and we know that the inverse of a relation has all the same points except the x's and y's are reversed, or in other words, we're essentially interchanging the domain and range. And you know that the line of reflection when you're looking at an inverse function is along the diagonal line y equals x. Algebraically, if you're trying to find the equation of the inverse, you're trying to interchange the x and y first and then try to solve for y in the equation. And we talked about that a little bit yesterday as well. Alright, in terms of some inverses that you know, okay, the inverse of a linear relation is a linear relation, and you can see that in the graph here. So the original function is the blue function here. That's the original linear function that I've graphed. And the inverse, as you reflect it along the line y equals x, is the red line that's drawn there as well. The inverse of a quadratic relation, so that's the blue graph there, is two root functions. So you have a positive root function at the top and a negative root function at the bottom. Okay, and you can see that it's reflected along that diagonal line. Okay, the inverse of an exponential function. We talked about this yesterday as well. So exponential functions are written in the form y equals b to the exponent x. And the inverse of an exponential function, when you interchange the x and the y, so you can see the x and the y have been interchanged, is an exponential function that depends on y. So the independent variable here is y and the dependent variable here is x. So you can see that the x and the y have been interchanged. Okay, graphically, depending on if the base is greater than 1, which would have an increasing graph, or if the base is between 0 and 1, you would have a decreasing graph. You can see that the inverse relation would also be increasing if it was an increasing graph to start with, or also be decreasing if it was a decreasing graph to begin with. Okay? And we saw this yesterday when you looked at the example with y equals 4 to the exponent x, and with the example where we had y equals 1/2 to the exponent x. Okay, so you saw how the graph of the original and the inverse were either both increasing or decreasing. Okay, the inverse of an exponential function. So, the inverse of an exponential function, x equals b to the exponent y. This is what it looks like when you're looking at the inverse of an exponential function. And so, normally when we're looking at any function, we like to have it as y equals something. Okay? So when we work with functions, we prefer to have the y coordinate of the function expressed in terms of the x coordinate. So y equals 2x, for example, or y equals x squared. We like to have y equals and then the statement that has the x coordinate. Okay? So what we're going to do is restate this relationship using what's called a logarithmic function. So we're going to take this inverse function that we know, and we're going to restate it using a logarithmic function. And here we are. So logarithmic functions. The inverse of an exponential function is written in the following two forms. So you either have it in exponential form or logarithmic form. So in exponential form, you know it as x equals b to the exponent y. But in logarithmic form, you have y equals log of base b to the a value of x. So y equals log base b of x. And so you'll notice that they share the same variables. The only difference is this is in exponential form and this is in logarithmic form. So x in exponential form represents the answer you get when you have a certain base to a certain exponent. In logarithmic form, the value that you get for the logarithm actually represents the exponent that you are solving for. X is the answer, and b is the base of the function that you had in the exponential form. So for example, if I had, let's say 10 to the exponent 2 equals 100. Okay, so we know the answer is 100. We know that the base is 10, and we know the exponent is 2. In logarithmic form, what this would look like is 2 equals log base 10 of 100. So you see that the answer is 100, and the exponent to which 10 must be raised to get an answer of 100 is an exponent of 2. So that's how you would write the same statement in exponential form versus in logarithmic form. They both mean the same thing. One is in logarithmic form and one is in exponential form. Okay? So logarithmic functions, the logarithm of a number with a base of b is the exponent to which b must be raised to get the answer x. So essentially, y represents the exponent that you are solving for. B is the base of the function, and x is the answer that you are going to get. So, in other words, if I write this, write another example. Let's say I have 125 equals 5 to the exponent 3. In logarithmic form, I know the answer is 3 because that's the exponent. I know I'm looking at the log of a base of 5. That was the base of the function that I had started with. And the answer is 125. Okay? So the log base 5 of 125 is equal to 3. Okay? Or in other words, 5 to some exponent will give you an answer of 125, and that exponent happens to be 3. When you're reading this statement, you read it as the logarithm of x to the base b, or log base b of x. One way to help you remember it is using this memory aid. The exponent is equal to the log of the base and the answer. So log base answer is equal to the exponent.